In topic 2, chapter 2, we learned all about motion in one dimension. We introduced the variables of displacement, velocity, and acceleration. We learned how to calculate them. We introduced the kinematics equations that allow us to study motion without worrying about the cause of the motion. In this new chapter, we continue our discussion of motion, of kinematics, but we move from one dimension into two dimensions. As you can see in this illustration, the jumpers move in two dimensions. The jumper moves along the horizontal axis, the x-axis, also moves along the y-axis, the vertical axis. If you try to follow the center of mass, you will find that the center of mass for the jumper moves along a parabolic path. So we will learn in this chapter how to analyze the motion in two dimensions. We'll come to this example later in this lecture. We are ready to move to kinematics in two dimensions. Usually, rather than describing the motion using one axis as we did before, the x-axis, now we need two axes, x and y, for example. We describe the original position by a vector, like the vector Ri, and the final position by another vector, like the vector Rf. So this is the initial position described by Ri. This is the final position described by Rf. The elapsed time here it was t initial, here it is t final. So the elapsed time is the difference between Tf and Ti. Now, from what we learned in chapter 1 for the addition and subtraction of vectors, delta r from this triangle over the three vectors, delta r is equal to Rf minus Ri. So this is the displacement. Delta r is the displacement vector because it connects the original position with the final position. Okay? We may decompose the displacement vector into x and y components. So this is the displacement vector, delta r. We can decompose it into a component along the horizontal axis, delta x, and another component along the vertical axis. The velocity is equal to this displacement per unit time, delta r divided by delta t. The velocity now has two components, one along x and the other along y. So the average velocity along x is delta x divided by delta t, and the average velocity along y is delta y divided by delta t. So you take delta x here, divide that by delta t to get the average velocity along x, and take delta y, divide that by delta t to get the velocity along y. The instantaneous velocity, we need to take the velocity when the time goes to zero, when the change in time is so small, infinitesimal. So that way we move from average value to instantaneous value. As for the acceleration, we need the change in velocity per unit time. So delta v divided by delta t, and again, we can decompose it into components, one along x and one along y. Ax equals delta vx divided by delta t, and ay equals delta vy divided by delta t. This is a typo. This should be vy, not vx here. Unfortunately, sometimes it's not easy to change things. Okay, fixed. And the instantaneous acceleration, we need again to take delta t to be 0, close to 0, in order to get the instantaneous acceleration. Which of the following objects cannot be accelerating? An object moving with a constant speed, an object moving with a constant velocity, an object moving along a curve. Any suggestion?
One.
Okay.
I would say number 2.
Number 2. That would be a better choice. Thank you. Because what is acceleration? Acceleration means either changing the magnitude of the velocity or its direction, right? So if it is a constant velocity means constant in both magnitude and directions. So when you see the word constant here before velocity, you understand that this velocity cannot be changed, cannot accelerate. Neither the magnitude nor the direction can change because we are told it's constant, right? While here, you can change the magnitude, and here, since it is on a curve, naturally it is changing all the time in order to be in a curve. The direction will be changing all the time in order to move on a curve. Thank you. Another question. Consider the following controls in an automobile: gas pedal, brake, steering wheel. The controls in this list that cause an acceleration of the car are. You have these suggestions. All 3 controls, the gas pedal and the brake, only the gas pedal. Remember the definition that we have for the acceleration? Acceleration means one of three things: either increasing the magnitude or decreasing the magnitude of the velocity, or changing its direction. So which one of these three can cause an acceleration? The gas pedal, the brake, and the steering wheel. Any suggestion?
I'll just throw this out there. I'd say one, maybe.
One. Thank you. Yes, it is one. Yes. When you press on the gas pedal, the engine speeds up. This is acceleration. When you press on the brake pedal, it slows down. This is deceleration, which is also acceleration but negative. When you rotate the steering wheel, you are changing the direction. Again, changing the direction of the velocity. This is also a form of acceleration. Any change in the velocity is an acceleration. So yes, the three controls. Another example. A girl on a bicycle takes 15 seconds to ride halfway around a circular track of radius 10 meters. What is the girl's average speed? You remember the definition for speed? Speed, you need the distance, divide the distance by the elapsed time. The distance is this arc, which is half the circumference, and the elapsed time, 15 minus 0 is 15 seconds, right? So what would be the speed, the average speed? You need your calculator, you need a pen and a piece of paper. When you calculate the average speed, distance divided by time, distance is half the circumference, so it's pi r. Pi multiplied by r, 10, divide that by delta t, 15. The answer is 2.09 meter per second. Do we agree on that? We are good?
Yes.
Excellent. Now, what is the magnitude of her average velocity? It's the same motion, but now we are interested in the velocity, not the speed. And as you recall, velocity depends on the displacement. So in order to calculate the velocity, you need the displacement involved here, and you divide the displacement by time. For the displacement, you need the original and the final position, right? So this would be the displacement vector, this diagonal. So for the average velocity, displacement divided by time. Displacement is the diameter that connects the original by the final points. The diameter is 10 multiplied by 2, it's 20, divide that by 15, so it is 1.33 meter per second. It is the same motion. As you can see, the average velocity is different from the average speed is different from the average velocity. So now I hope that we all have a feeling for these quantities and how they are different from each other. They are related, but they are different from each other. We move on to velocity in 2 dimensions. Suppose you have this displacement, this motion, 15 meter. Okay. So you may decompose this into x and y components. X would be 30 and y is 40. So the path length is 30 plus 40, which is 70 meters. Okay, but the displacement is 50 meters. So this is another illustration for the difference between displacement and distance. This is distance, which is 70 meters. This is displacement. So now average speed, if this motion occurred during 20 seconds, average speed, you will take the distance 70 divided by 20, it's 3.5 meters per second. And average velocity, you take the displacement 50 divided by 20, it is 2.5 meters per second.